So, in the last class we started the topic Bode stability criteria. We will continue that topic and we took one example also. So, today we will continue Bode stability criteria with that example. Bode stability criteria. We considered a P only controller having transfer function K C. We considered the first order plus date time system for the process, and the transfer function is exponential of minus 0.123 s divided by 0.1 s plus 1. For simplicity, we considered GM GF both equal to 1. First, we need to write the open loop transfer function, that we can write as K C divided by 0.1 s plus 1 exponential of minus 0.123 s. This is first order and this is date time part. So, the expression for phi we can write as tan inverse minus 0.1 omega minus 0.123 omega multiplied by 180 degree divided by pi. This is the expression for phi. If we consider phi equals minus 180 degree, then we obtain omega equals 17 radian per minute. Here time is in minute. Now, this is basically crossover frequency. Crossover frequency or critical frequency is the frequency which is calculated at phi equals minus 180 degree. In the next step, we can write the expression for amplitude ratio, that we can write as K C divided by tau square omega square plus 1. Here tau is 0.1, omega we are considering crossover frequency, whole square plus 1. Then we obtain amplitude ratio divided by K C equal to 0.5. We obtain amplitude ratio divided by K C equal to 0.5. Now, we obtain amplitude ratio 1 when K C equal to 2. We obtain amplitude ratio equal to 1 when K C equal to 2. So, we can say that amplitude ratio we can obtain greater than 1 considering K C greater than 2. Similarly, if we obtain amplitude ratio less than 1 when Kc less than 2, fine. So, Kc equals to 2, that is the critical value of Kc, 2 is the critical value for Kc. I hope up to this we discussed in the last class, fine. So, today we will start with the open loop response. Next we will find the open loop response of the example system. Now, how we can open the loop? Previously we considered the closed loop, we want to open that. Then we need to disconnect something, and that is shown here. This is the block for first order plus date time system. Output is y bar. This is the comparator, this is set point, and this is measuring device. Negative, this is positive. Now, we are disconnecting the measurement signal from this comparator, fine. Then we can say that this is open loop. Fine. We wish to know the open loop response by disconnecting the measurement signal from this comparator. In addition, we will consider the followings. First, we will consider amplitude ratio equal to 1, phi equal to minus 180 degree, fine. If we consider phi equal to minus 180 degree, we obtain crossover frequency is 17 radian per minute, agree. If we consider phi equal to minus 180 degree, we obtain crossover frequency 17 radian per minute. Now, at this crossover frequency, we obtain Kc equal to 2 at amplitude ratio equals 1, fine. So, this is our first consideration, amplitude ratio equal to 1 and phi equal to minus 180 degree. Secondly, set point changes in a sinusoidal manner. Set point changes in a sinusoidal manner with omega equals 17 radian per minute and input amplitude equals 1. This is the second consideration. Set point changes in a sinusoidal manner with omega equals 17t and input amplitude equals 1. That means, this is sin 17 t. Fine. So, in time domain I can write this y set point equals sin 17 t. Here we can write y set p equals sin 17 t. Then how much is the error signal? Error is also sin 17 t, because we have disconnected this measurement signal from the comparator. So, error signal is also sin 17 t, which is equal to y set point, and they are written in time domain. Now, our first consideration is amplitude ratio equals 1. Amplitude ratio equal to 1. Amplitude ratio is nothing but output amplitude divided by input amplitude. Fine. Again we considered in the second consideration input amplitude equals 1. So, how much is output amplitude? Output amplitude becomes 1. So, if the input is changed in sinusoidal manner, what is the output? Output is A out sin omega t plus phi. This is the output. This is the output. So, amplitude of this output wave is 1, omega is 17 and phi is minus 180. We have considered in our first point phi is minus 180. That means, this is minus sin 17 t. Agree? So, if we introduce set point change in sinusoidal manner, the output is minus sin 17 t. This is also sinusoidal. So, we can write y m equals sin 17 t. Fine. This is the open loop response when the process is subjected to a change in set point in sinusoidal manner. In the next, we will discuss the closed loop system response. In the next, we will discuss closed loop system response. So, we will consider two events at a time. I mean, we will consider at the same time two events. They are no change in set point, no change in set point. That means, y set point equal to 0. At the same time, we consider another point, that is close the loop. This is the second point. So, what will be the corresponding block diagram then? Controller is this one, final control element is has the transfer function of unity, lossless transfer function is exponential of minus 0.123 s divided by 0.1 s plus 1 y bar gm equal to 1, comparator y set point equal to 0. This we are simply connecting the measurement signal with this comparator. So, this is the closed loop system. Here we are considering no set point change and we are closing this. The output signal was minus sin 17t, fine. In the previous block diagram the output was minus sin 17t and we are suddenly closing it, and at the same time we are not introducing any change in set point. So, this is negative, this is positive. So, how much will be error now? Sin 17t. So, you notice that the error remains the same. In the open loop system, error was sin 17t. When we are closing this loop and we are introducing no change in set point, we are getting same error signal, that is sin 17t, fine. So, error is sin 17t and we are getting output minus sin 17t. What it indicates? Sustained oscillation. I mean, if we consider Kc equal to 2, then amplitude ratio is equal to 1. When phi is equal to minus 180 degree. If Kc is equal to 2, which is the critical Kc value, then amplitude ratio equal to 1 when phi equal to minus 180 degree. And in this situation we obtain sustained oscillation, I mean oscillations with constant amplitude, oscillations with constant amplitude. What about stability? If we obtain sustained oscillation, what about stability? Marginally stable, we can use this term, marginal stability, fine. Now, similarly we can conclude that if Kc is greater than 2, then amplitude ratio greater than 1 when phi is minus 180 degree. If Kc is greater than 2, then amplitude ratio becomes greater than 1 when phi is minus 180 degree. So, what type of response we can obtain in this condition? Oscillations with increasing amplitude, oscillations with increasing amplitude, fine. Then what about stability? Unstable. Similarly, if Kc is less than 2, then amplitude ratio less than 1 when phi is minus 180 degree. If Kc is less than 2, then amplitude ratio becomes less than 1 when phi is minus 180 degree. So, in this condition we obtain oscillations with decreasing amplitude. Oscillations with decreasing amplitude, and this is stable. Fine. Now, based on this observation, we can write the Bode stability criteria. That is, a feedback control system is unstable if the amplitude ratio of the corresponding open loop transfer function is greater than 1 at crossover frequency. Bode stability criteria is stated as a feedback control system is unstable if the amplitude ratio of the corresponding open loop transfer function is larger than 1 at the crossover frequency. This is the Bode stability criteria. Fine. A feedback control system is unstable if the amplitude ratio of the open loop transfer function is larger than 1 at the crossover frequency. Next, we will discuss the stability analysis based on this Bode criteria. We will take a number of examples and we will apply this Bode stability criteria. So, our topic is stability analysis based on Bode criteria. Stability analysis based on Bode criteria. First, we will consider a first order process. First order process. For a first order process, we can consider the transfer function as Kp divided by tau Ps plus 1. This is the transfer function of a first order system. We consider P only controller. So, Gc equals Kc. This is the transfer function of P only controller. For simplicity, we consider Gm and Gf both equal to 1. Fine. Now, at the first step we need to find the open loop transfer function. The open loop transfer function for this example system we can write as GC GP GF GM, and that is equal to Kc Kp divided by tau Ps plus 1. Fine. And we can write this as K divided by tau Ps plus 1, where K is Kc Kp. K is Kc Kp. Now, what about the phi? If we consider omega equal to 0, how much will be phi? Phi will be 0. This is a first order system. I mean, this is the transfer function of a first order system. When omega is infinity, how much is phi? For a first order system, minus 90. When omega is 0, phi is 0. When omega is infinity, phi is minus 90. Fine. For a first order system, phi remains in between 0 and minus 90. So, what it indicates? Phi is always greater than minus 180. Agree? Phi is always greater than minus 180 degree. That means there is no existence of crossover frequency. No existence of crossover frequency. So, what about stability? Stable. If there is no crossover frequency, then the system always remains as stable. So, for a first order system, the process always remains at stable state irrespective of the Kc value. Only thing is that if you consider large Kc, then oscillations will be more, but there is no instability problem. So, we can say that first we need to check whether crossover frequency exists or not. So, first we need to check it, crossover frequency exists or not. If the answer is no, then the system is stable. If the crossover frequency does not exist, then the system is stable system. So, you can use any Kc value, at least there will not be any instability problem, but as I mentioned, with the increase of Kc value, the oscillations also, the response also becomes more oscillatory. Now, if the answer is yes, crossover frequency exists, then instability problem is there. Instability problem is there. So, how we can make it stable, this unstable system? We can make it stable by tuning the controller. We can make this unstable system stable by tuning the controller. So, if there is any instability problem, tune Kc, fine. So, initially we considered the first order process, in the next we will consider a first order plus date time system. Next we will discuss a first order with date time process. Transfer function of a first order plus date time system we can write as Kp exponential minus say 0.15 s divided by tau Ps plus 1. Here date time is 0.15. So, this is the transfer function of a first order plus date time system. This is the transfer function of a first order plus date time system. Here we are considering Gm equal to Km. Controller is P only controller. So, Gc equals Kc, and for the final control element Gf is equal to suppose Kf, fine. So, these are the individual transfer functions for the example system. Now, we need to write the open loop transfer function. What will be the open loop transfer function? Kc, Kp, Kf, Km exponential minus 0.15 s divided by tau Ps plus 1. This is the open loop transfer function. So, this transfer function we can rewrite as K exponential of minus 0.15 s divided by tau Ps plus 1, where K is Kc, Kp, Kf, Km. Fine. So, this is overall the transfer function of a first order plus date time system. Now, what will be the expression for phi? What will be the expression for phi? Phi will be tan inverse minus tau p omega. This is for the date time free part, and for date time part the phi will be minus 0.15 omega, fine. This is for date time free part and this is for date time part. Now, we can multiply with 180 degree divided by phi, fine. Now, when omega tends to 0, what about phi? If omega tends to 0, then phi tends to 0 degree. When omega tends to infinity, what about phi? Phi will be minus infinity. Agree? If omega tends to 0, then we can write phi tends to 0 degree, and when omega tends to infinity, phi tends to minus infinity. So, what about crossover frequency? Crossover frequency exists. Now, at large value of Kc, amplitude ratio may become greater than 1 at crossover frequency. At large Kc value, amplitude ratio may become greater than 1 at crossover frequency. It clearly indicates there is an instability problem. So, first point is the crossover frequency exists, and at large Kc value the amplitude ratio may become greater than 1 at crossover frequency. That means there is some instability problem. So, overall we can say that dead time is a principal source of destabilizing effects in chemical process control systems. We can conclude based on this example that dead time is the principal source of destabilizing effects in chemical process control systems. Fine. Now, when we started the Cohen-Kuhn technique, it was mentioned that the response of most of the chemical processes can be approximated by the response of first order plus dead time system. When we started the Cohen-Kuhn technique, it was mentioned that the response of most of the chemical processes can be approximated by the response of first order plus dead time. That means almost all chemical processes have instability problem due to the inclusion of dead time part. Fine. So, we can say that almost all chemical processes include the dead time part. That means almost all chemical processes have instability problem. Now, as mentioned before, to make it stabilize, we need to tune the controller. We need to tune the controller. So, controller tuning becomes a crucial task. Controller tuning becomes a crucial task. Fine. Next, we will consider a third order system and we will apply the Bode stability criteria. Higher order systems. Yeah, before third order system we will consider second order system. We will consider next second order system, then third order system. So, the transfer function for a second order system we can write as Kp divided by tau Ps plus 1. Now, this is the transfer function of a first order system. Now, we are considering Gf equal to Kf, we are considering Gc equal to Kc and Gm equal to Km divided by tau ms plus 1. Fine. These are 4 individual transfer functions. Now, overall transfer function we can write as K divided by tau Ps plus 1, tau ms plus 1. Can we write this? Overall transfer function becomes K divided by tau Ps plus 1 multiplied by tau ms plus 1. This is the second order system. I mean, this is the transfer function of a second order system, and obviously here K equal to Kp Kc Kf Km. Now, if we consider omega equal to 0, how much is phi for the second order system? 0 degree. We are not writing the expression for phi because we discussed this several times. When omega is equal to 0, for the second order system phi becomes 0 degree. When omega tends to infinity, phi tends to minus 180 degree. Fine. For the second order system, the phi varies from 0 to minus 180 degree. So, what about the existence of crossover frequency? What about the existence of crossover frequency? There is no existence of crossover frequency at finite value of omega. There is no existence of crossover frequency at the finite value of omega. That means there is no instability problem. No instability problem. So, see, first order system without dead time, no instability problem. Second order system without dead time, no instability problem. Next, we will consider the third order system. So, next we will consider the third order system. Suppose the transfer function of the process is Kp divided by tau Ps plus 1. Transfer function for the final control element is considered as Kp divided by tau Fs plus 1. Controller is P only controller, and the transfer function for the measuring device is considered as Km divided by tau Ms plus 1. These are the 4 individual transfer functions. So, obviously, the open loop transfer function becomes third order transfer function. I mean, we can write it as K divided by tau Ps plus 1, tau Ms plus 1, tau Fs plus 1. This is the open loop transfer function for the example system. Now, when omega is equal to 0, phi becomes 0 degree, and when omega tends to infinity, phi tends to minus 270 degree. So, for a third order system, the phi varies in between 0 and minus 270. So, what about the crossover frequency? Crossover frequency exists. So, there is instability problem. Fine. So, we can note one point that up to second order system, if there is no dead time, the systems do not have any instability problem. First order system without dead time, no instability problem. Second order system without dead time, no instability problem. Third order system without dead time, instability problem is there. So, up to second order, there is no instability problem if there is no dead time. But if dead time is there, from first order system itself, instability problem arises. fine. Next we will discuss another topic under this frequency response analysis, that is gain margin and phase margin. Gain margin and phase margin. This gain margin and phase margin are the typical performance specifications associated with the frequency response analysis. Gain margin and phase margin are the performance specifications associated with the frequency response analysis. Fine. So, for discussing this gain margin and phase margin, it is better to consider an example, and we will continue the example which we considered earlier, having the open loop transfer function equals Kc exponential minus 0.123 s divided by 0.1 s plus 1. To discuss the gain margin and phase margin concept, we consider this example, where Gf and Gm both are equal to 1, and the transfer function for the process we consider exponential minus 0.123 s divided by 0.1 s plus 1 and Gc equals Kc. Recall the fact that if Kc equal to 1, if Kc equals 2, then amplitude ratio becomes 1 when phi equals minus 180 degree. We concluded this for this example earlier. If Kc is equal to 2, then amplitude ratio becomes 1 when phi equals minus 180 degree, and this corresponds to marginal stability. Fine. Okay. Now, at phi equals minus 180 degree, we know that at phi equals minus 180 degree we obtain the crossover frequency. So, we will try to show it in the Bode plot. This is omega, this is phi. Now, the plot is say like this. This is suppose 0 degree and this is suppose minus 180 degree. Fine. So, at minus phi equals minus 180 degree we obtain crossover frequency. Agree? So, the frequency corresponding to this phi equals minus 180 degree is crossover frequency, which is shown in this figure. Now, above this we will draw amplitude ratio versus omega. Suppose this AB curve we obtain for Kc equals 1. Fine. This AB curve, I mean this is the amplitude ratio versus omega plot we obtain considering Kc equals 1. That means the Kc value we have taken lower than the critical Kc value. Now, at this crossover frequency, how much is this value? At crossover frequency, amplitude ratio is suppose m. Agree? And critical value of Kc is 2. Suppose this is the amplitude ratio versus omega plot when Kc equal to 2. So, at crossover frequency, how much is this amplitude ratio? 1. Fine. So, when omega equals omega CO, we obtain amplitude ratio equal to m, which is lower than 1. Agree? If we obtain 1, then marginal stability. If this is lower than 1, that means stable system. So, when omega equals omega CO, I mean at crossover frequency, if amplitude ratio is less than 1, then that is the indication of stability. So, we can say that the response is stable response when Kc equal to 1, because at crossover frequency amplitude ratio is less than 1. I am repeating again the steps. This is phi versus omega plot for this example system. Now, crossover frequency is the frequency which is obtained at phi equals minus 180. So, we consider phi equals minus 180, corresponding omega is crossover frequency. Now, for the example system, we know the critical value of Kc is 2. Here we first consider Kc equals 1, I mean it indicates stability. Now, AB is the amplitude versus omega plot when Kc equals 1. At crossover frequency, it is clear from this Bode plot that amplitude ratio is m. Then we can make another amplitude versus omega plot at the critical value of Kc, that is 2, and at crossover frequency the corresponding amplitude ratio is 1. So, it says that when we consider Kc equals 1, amplitude ratio less than 1 at crossover frequency. Now, this difference is the gain margin. You see, this is nothing but a safety factor. This difference is called the gain margin, and this is nothing but a safety factor. Okay, in the next class we will discuss the phase margin. Okay.